Hello everybody, this is lecture 8 of the course Electromagnetic Theory. I am Amr Abdul Bari with Nearest University. Today I continue or speak about the steady current and how we can prove or reach the Ohm's law. Stationary charges produce electric field that are constant in time. So steady current again produce a magnetic field which is are constant in time. This is the meaning or the term magnetostatic. Okay, so the stationary charge produce the electric field, the steady current produce magnetic field. So by steady current we mean a flow of charge, some charges that it's there forever, not increasing, not decreasing. The charge distribution is meaning that the charge in motion they constitute the current distribution, and this current density, having a current density rho v, in having the charge move, giving a current, the current or this charge move with a velocity u dash through a surface delta s, which is normal, having the normal surface normal is n hat. So over a period of time delta t, delta L is equal u, the velocity, delta t, and the charge is rho v delta v. So it's equal to rho v u delta t dot the n dash delta s. Okay, so the current, this is the charge, the change in the charge or the amount of charge that's crossing some surface. The corresponding current is the charge over the change in the current over the change in the time. So it is rho v u dot n v n dash on n hat delta s. The current density is the current in a space or in a surface or in a volume. So it's rho v u only. So the total current, here we measure a small change or a small part of the current. The total current is by taking the integration over all the current density in this surface that come across a surface. So if this surface is a closed surface, then you can take the closed integration over this over the density and you get the I. For a steady current, it should the change or there is no change, so the closed surface should equal to 0. This means that the net current through a closed surface is 0. Okay, the gradient of a j is equal to 0. So by now you know that there is two type of current, electrical current. One which is due to the motion positive or negative charge in a vacuum or a gas, and the second one is due to the move or the motion of the charge in a conductor or a semiconductor by the moving of the electrons or holes. This is will lead to the Ohm's law. Okay, so this is two type of electric current. The conduction current, we are interested in the conduction current, which is current in a conductor or a semiconductor. The velocity is equal to minus mu e. Mu e is the electron mobility, which is the unit, takes the unit m square over v dot s. In the semiconductor is mu h, and h is the whole mobility. So the current density is equal to rho v u, rho v for the electron and rho v for the holes. So you can take it as all as a value here, multiplied by the E, the electric field. Then here you can they assume that this value is related to the material. We call it the conductivity of the medium, or it's measured in units Siemens per meter or moles per meter. In either case, J is equal to rho E ampere per meter square. This is the current density, and this is the field theory expression of the Ohm's law. Now, it can be said that in a perfect dielectric there is no any conductivity, so rho is 0 and J is 0. In a perfect conductor, this is meaning the perfect conductor, is rho should be go to infinity and E is J over infinity, so it should be 0. However, the materials is in between. It's having a finite number for the conductivity, which is for the conductor, different material of the conductor. For example, for semiconductor, for a pure germanium, its rho is equal to 2.2. For the insulator, it go up to it go down close to 0, 10 to the power minus 10 or 10 to the power minus 17. So the Ohm's law for a linear homogeneous conductor of length L, this is the length L of a conductor, and this is the surface that we speak about, and the current come from current or a voltage source. So the electrons that come from the source is pushing the equilibrium here. There is equilibrium when there is no any connected by a wire to the current source. So the charge prevent the equilibrium, and there is of course a electric field will be exist, and therefore there these electrons, as they move, they will encounter some resistance. Okay, so resistance is based on the S, the cross section area, and the length of the conductor. As here E is equal to V over L, the electric field is equal to the potential over L, and the J is I over S. So this, since I is equal to the integration of J dot S, so, and again J is equal to rho sigma E. So if you take the equation here, J is equal IS and J is equal rho E, and so you substitute E here and substitute the J here, so I over S is equal rho V over L. So you can take from rho R from Ohm's law, R equal V over I. So V over I is L over S rho. This is the Ohm, this is the resistance, and this is what we know. So it's depending on the conductivity and the length of the conductor and the surface of the conductor, the surface area, section area. Now the electrons is moving in the conductor or drift in the conductor. The atoms have some energy, a kinetic energy of the electron is converted to a thermal energy because of the collision with the atom. Okay, so this energy or this kinetic energy is dissipated in the conductor as a heat. So as the current increase, there is a heat increase in the conductor due to the electric current that come across the conductor. Okay, so we see that this dissipated power is equal to the integration of J dot E delta V in watt, of course. And if you put J is rho E, so it is the integration rho E square delta V. This is the dissipated power in a conductor. Now let's see the conservation of the charge or the continuity equation and Kirchhoff current law. Now the equation of continuity, it's the mathematical expression is a fundamental fact. Okay, so assume that we have a total charge inside S, which is equal to Q in at time t, and the current is equal to the integration over J dot S in this surface, so it's equal to the change in the charge in time. it's minus the change in the charge. Okay, so the charge is equal to the charge density in the volume, and so you can put Q here. So the integration over the current density is equal the change of the charge density. Okay, so as the charge density or a number of charge in a space or a volume in change, there is happening meaning by change, meaning that they move, or they the number of the density here is in large, there is a change over time. So this meaning that the current density also change. Okay, this is the integral form of the continuity equation. So here in the left hand we can make the gradient, okay, of J, and in the right hand we can take this is inside for stationary volume if the volume doesn't change. So you can say that if you take this into the other side, that gradient of J, you can remove the integration from both sides and say that this is a continuity equation. Gradient of J plus the change in the charge density is equal to 0, which is a concept. It's obvious. This is a continuity equation. For a steady current, the change is equal to 0, and then the delta J is equal to 0. Field theory expression of the Kirchhoff law is that the integration over S over the surface of the current density is equal to 0, and the theoretical part is that you take the summation over all the current inside this all the current. If you take the summation, it's equal to 0. Now let's see the boundary or the boundary condition for the steady current. As we all know that we have a boundary of two material with two conductivity and two permittivity, rho 1 and rho 2, epsilon 1 and epsilon 2. Now assume the positive unit normal is from medium 1 to medium 2, and then apply the equation to Gaussian cylindrical surface. J to n is equal to J1n, which implies that rho to E to n, the normal, is the same for the second, from first to the second. Nothing here happened. So here applying the equation to a rectangular path, it's evening that the tangent is the same, the tangent field effect, and the J21 tangent over J1t is equal to rho 2 over rho 1. Okay, the resistance of the two electric material of the capacitance and the relation between them, between the resistance and capacitance, here the C is equal to QV as we know, and unit farad, and the resistance is VA over R. So if you took the multiplication in both of them, RC is equal to Q over VI. So the V will go with each other, so the rest is Q over I. So if you put the integration, then form integration over surface epsilon E, integration over surface rho E. So epsilon E will go, and the left is epsilon over rho. So this is an important result since C gives R immediately. So this is a value that's related to the material itself, not really depending on the electric field or the charge in these materials. Okay, so that's it for today. Thank you for listening.